Okay, so today we're gonna study how to formulate a deep perceptron for the XOR gate. We have seen in the previous lecture that the simple linear perceptron cannot model the XOR gate because a simple binary classification is not enough for the XOR gate. And this is basically the linear perceptron, and to understand why the linear perceptron is not enough for the XOR gate, let's consider the truth table of XOR, which we have the inputs and the outputs. So basically, when they're both true, it's going to be -1, +1, -1 is going to be true, -1 +1 is going to be true, and -1 is -1 is going to be false. So the difference with the OR gate is that either we can have one winner, but we cannot have two winners at the same time. That's why here. That's basically the XOR. And we have seen that if we plot the data points, when we want to train our linear perceptron to find the weights and the bias, so we need the data points, which are given by pairs of an input and a label. In this case, is the output y for n equal 1, 2, 3, and 4. So the data points this is 1, -1, -1, and 1. The data points, so for example, 1 and 1 is here, and this is true. So we're gonna do true outcomes with a full circle and an empty circle for false. And so +1 and -1 is down here. Okay, no, okay, this is basically false. And this is gonna be true. And so these are true results, -1 and +1, this is also true, false, and then -1 and 1 is false. So you see that there is no way to draw a decision boundary, in this case, a line, to separate the false outcomes from the true outcomes. Actually, to do that, we need two decision boundaries. One for which, the outer region is gonna be the false results, and the inner region will be the true results. And it is clear that this kind of decision boundary, can follow basically from a quadratic law, in which these are the positive results and here the minus results. So basically, that's how you. What does it mean? I mean, in order to model the perceptron, to model the OR gate, the linear perceptron is not enough, and so we need something. We need an nonlinear perceptron. Specifically, in this case, even a quadratic perceptron will work. What does it mean? That now the decision boundary must follow from a quadratic law, and for example, I mean, we can choose a perceptron, a quadratic perceptron that has the following, is given by w dot x plus b square plus alpha. So we will need a quadratic perceptron that will be able to give us this kind of decision boundaries. However, we can formulate the same problem in a different way that basically lead us to the concept of a deep perceptron and neural network, and that's why and that's what I'm gonna do in the following.